Good morning or afternoon or whatever it is where you are. This is the first of three little videos. What have you had on today? This is my kind of Hawaiian shirt, Snow. My mom made it for me a long time ago. It's kind of wild. well, yes, it is, but I kind of like it. It's festive. I like it. Oh, thanks, Om. Yeah. So I decided it's the weekend. Why not? Dad, it's okay, Snow. It'll be fine. I'll wear a more conservative shirt next time. I like it. Yeah, thanks, Om. But today we got some work to do, and so why don't you guys have a seat and we'll take a look. So the first problem I want to talk about is a traffic flow problem. It is in section 1.3, it's example 1. So I decided to do examples that are in the book. Here's the idea. This is a town square, so people can drive around it. And you monitor the traffic on the outside. So here's 100 cars coming in a 15-minute period, 20 cars leaving this way. And so on these roads in and out, you have a certain amount of traffic that you have measured, and you want to get the idea of what the traffic is likely to be on these roads that are right around the town square. So you've got the intersections here, A, B, C, D, which I've located. The unknown traffic are the traffic around the square, X1, X2, X3, and X4. So we want to solve the equations that we get as we balance the traffic at each of the intersections. So in order to balance the traffic, for example, at flow A, the flow at A, the incoming traffic is 100 and X1. And the outgoing traffic is 20 and X2. And input equals output at each node. So 100 going in, X1 going in, that's the in, 20 out, X2 out. At node B, the input is X4 and 30. And that will equal the output, which is 100 and X1. So we want to do this at all of the different nodes. So we also want to do it at C, and I'll put it in a different color here, and at D. So at C, the input is X2 and 25. This will be equal to the outflow, which is 95 and X3. And at D, the inflow is X3 and I guess that's it. Let me make sure I've got the arrows right. I do not. The 75 is inflow as well. So the inflow is X3 plus 75. And the outflow there is X4 and 15. So you've got 4 equations, 4 unknowns. We'll take a look at the solution. And before we do it, I'll write the final equations that I get. So the equation 1 is X1 minus X2 equals minus 80. I want to put this in an augmented coefficient matrix, so all the constants on one side, variables on the other. X1 minus X4 is equal to 70. X2 minus X3 is 70. And X3 minus X4 equals minus 60. make sure I have those right. X1 minus X2 is minus 80, yes. And then from this one, X2 minus X3 is 70. On the third one, here we get X4 minus X1. Oh, I guess I did it the other way. X1 minus X4 is X1 minus X4 should be minus 70. And X3 minus X4 should be minus 60. So these are correct. And on the sheet that I gave you, it's a Mathematica sheet. I have the rest of this. So I put down the AC matrix, the augmented coefficient matrix, row reduce with Mathematica, and then write the solution. And when we write the solution, you will find out that there is a free variable here. And for example, the X1, I believe, ends up to be S minus 70. So S can be anything, but because of the nature of the problem in the solution, X1 has to be bigger than or equal to 0. You do not allow traffic to back up. So there are conditions here on the solution that have nothing to do with the arithmetic of getting the solution. They have to do with the original problem. So this gives you an additional condition that X1 or S has to be 70 or bigger. And I think that's the only condition on this problem. So that is what I wanted to say about the traffic flow problem. Look at the Mathematica sheet, look at how the setup goes, and that is traffic flow.